and then we try to look at, and we mentioned that once we are talking about ideologies and how these ideologies can be converted into equations, we should look at what we call a variable. We'll come to that. We should look at what to call variable, and under the variable, I was able to explain. We were able to explain the meaning of variable, and we said a variable is anything that changes in magnitude. And then I asked if you should go and find out if you say a variable, it doesn't only mean changes in magnitude, it can also mean changes in kind. And I was able, you were asked to go and do your research to find out when we say a variable changing in kind, what does it mean? And what are some of the examples? Have you found out?
Yes, sir.
Yes, so example, can you mention your name and then tell me what you have found?
This is Lawrence, sir.
This is who? Lawrence.
Yeah, sir.
Okay, so go ahead.
So the example, we have gender, that is male and female.
Yes, exactly. And then there is no only gender. That is what you have. Is it only gender you have found?
No, sir. I also find the economic system. We have the capitalists, we have the socialists, and then we have the mixed economy. And I also find out the type of goods. We have consumer goods, capital goods, and then types of occupation.
Okay.
Yeah.
Okay. So someone else, or you say you've also found the same thing? Yes, someone else. Lawrence has done well. He has really done search on the variable that we were talking about. Who else wants to say something? If you want to talk, just unmute yourself and talk. If you raise your hand, I might not see you. Yeah.
Yes, sir.
Mm-hmm.
Please, I'm Prince Obi.
Prince Obey, go ahead.
Yes, sir. Please, can I also mention taste and preference?
Come again.
Can I also mention taste and preference?
Taste and preference. Okay. Yeah. Yeah. Is that the only thing you found out?
And also something like fashion and then weather condition.
Yes. Okay. Yes, that's okay. So that is good. So all the things you've mentioned are all variable that change in kind. You may not see them changing in values, but they change in some way, one way or the other. A perfect example is the gender that Lawrence mentioned. You can also mention hair color. Okay, you can also mention ethnicity. Okay, you can also mention religious bodies. Religious. So they are all variable that changes in kind. In statistics, we call them nominal variables. Nominal variables. Okay. Now, once we know what a variable is, now when we talk about the model always try to connect the variables together. To connect the variables together. So we have something we call the independent variable, and then the dependent variable, or you can say the exogenous variable and then the endogenous variables. Now we have to look at them one after the other. What is exogenous variable, or what is independent variable? The independent variable does not depend on any factor. It is independent on its own. It does not depend on anything. It stands alone. Okay. So guys like Ghana, once a while, years ago, were dependent, were under we are under rule by some people. So we are dependent on those people. But now we are independent. We depend on ourselves. Okay. And then when we talk about the dependent variable, there are also variables that depend on other factors. Without other factors, those variables cannot survive. Okay. So if economically, if we say a dependent variable, it is a variable that is being determined by the model. Remember that we know what a model do. A model try to explain or translate the theories, the ideologies into what? Equations. Okay. Now, the dependent variable dependent variable will be determined within the model. Okay. But the independent variable will be determined outside the model because it is independent. It doesn't have to depend on the model. It's dependent outside the model. So basically, these are the two type of variable that we have. Okay. Then we move on to look at, before we can link the two variables together, that is the exogenous variable and then the endogenous variable, or the independent variable and then the dependent variable. Then we can look at some of the categories that will link the two variables together. Okay. Now, let me give you an example of the dependent and the independent variable before we move on. We said the dependent variable depends on other factors, or they are determined within the model. And then the independent variable are determined outside the model, or they are independent. They don't depend on any factor. Okay. For example, if I say your class scores is related to your hard working or night of study. So I have class score and night of study. Okay. Now, if you want to relate this one to independent and dependent variable, which one do you think will be your independent variable? Which one do you think will be your dependent variable? Night of study and then your class scores. Who can help? If you want to talk, just start talking, because if you raise your hand, I might not see you.
Hello, sir.
Yes.
I would say that the class score is a dependent variable, then the night studies is an independent variable.
That's correct. So then it means that how much scores you will get in the class depend on how many nights you spend studying. Okay, so the class score is your dependent variable, and then the night of study is your independent variable. Now it means that the night score, your class score depends on how many hours you spend on studies. So it depends on something. But the night score, so when we look at these two here, the dependent variable is determined within these two models, the class scores and then the night score. It's determined within these two models. So we call it dependent variable. But if we look at the night of study, okay, even though there are other factors that will determine your night of study, that factor is outside the two models that we have. Okay, that factor is not between these two models. It is outside these two models. Okay, you can measure other factors that might have influence on your night study, but it is not within these two models, class scores and night of study. These are the two models we are talking about. Okay, but within these two models, we realize that your class scores depend on your night study. So the dependent variable is clearly stated within the model. But if you look at the night score, the night of study, we realize that you cannot find any factor within the model that influence your night study. Okay, so because of that, we are saying that that variable is determined outside the model, and that is what we call the independent variable. And for us to connect the night score and then the class, the night studies and the class score together, then we have to take note of the categories that will link the two together. Okay, remember that the model that we stated, we can use equations to specify them. Okay, before we use equation, we have to look at the three categories. The first category is that we have to look at the definitions. So when we talk about the definition or identity, we are trying to look at how two variables are identical or are a function of the other variable. Then we'll look at, for example, if you have, let me use my pen. For example, if you have, let's say, total revenue, for example, if you have total revenue, so, or even profit, if you have profit, what is the definition of profit? Profit is equal to total revenue minus total cost. And the total cost. So we are saying that this is a definition. So this total revenue minus total cost define our profit. Define our profit. So before we can relate two variables, we should look at whether the two variables are definable. Whether they are definable first. Okay. Then there are other definitions that you can look at that try to explain the relationship between what two variables. So here we are relating to profit to what total cost and total revenue. Okay, so there are other things that you can also look at. So the definition that I was talking about, so like I was saying, profit function, we can try to define profit function is profit is defined as what? The differences between total revenue and total cost. Now here we have to take note of the word identity. Identity. So when we say something is identical, it doesn't mean they are equal, but they have some kind of similarity between them. Okay. And I use the example of total revenue and the profit function to define that the profit is being defined by two components, that is total revenue and total cost. Even you can even use the model that our consumption plus our investment. This is the definition we are talking about. So it tells you that before you can link the dependent variable and the independent variable together, you should first of all know the definitions, whether they are being defined, whether they are related. Yes, before we connect the real equation, the behavior, modeling people actions, modeling people behavior, or representing people behavior and action using the economic principles. So we try to look at the dependent and independent variable and see if we can try to replicate this one using human behavior. Okay, so we can also use the behavioral equation to try to connect the two variables together. Okay, now example of the behavioral equation. So equation that try to explain human behavior, equation that try to represent human actions or economic agent actions. So if you look at the demand equation that we've been looking at, it's a typical example of the behavioral equation, because the demand equation try to define how people behave, behave towards the quantity demanded of a commodity and then the price of a commodity. Okay, so we said at a higher price, lower quantity is being demanded. What is the essence of this? So it means that people are being sensitive. People behave towards, people take actions towards what? The changes in prices. So if prices are high, people behave, or people put some action towards the higher prices. So they try to what? React to the change in prices. So that is the behavior of the people when prices change. Okay, so for us to represent this one using the model, we use the behavioral equation to what? Represent their actions. Okay, so we can look at other equations that can represent the behavioral equations. We have the investment, the money demand, even the consumption function. It's very, very important that depict the behavioral equation. So these are some examples of the behavioral equation. The behavioral equation, we said that it tries to represent a model economic agent actions or people rat actions. So if you look at the consumption function, which was also propounded by John Maynard Keynes, and he said that when he was studying about consumption, he wanted to look at the link between consumption and income. So he found that when your average income, or when your income increases, people also react to what? How much they consume. So when your income increases, people behavior changes in terms of how much they are going to consume. Okay, so we use the behavioral equation to model that by coming out with an equation to also try to predict this behavior or study the behavior of this kind of people. So these are all examples of behavioral equations. So this behavioral equation can be captured in a variable form. So from there, we can be able to determine which one is the dependent variable, which one is the independent variable as we move on. So we can use equations to represent the behavioral ones as well. Okay. Please, if we are going and you think you have something to say, guess have to let me know, then we address it and move on. Okay. So we now move to one last category, is about the equilibrium condition. Okay. Now that we are able to establish the two variables together, now that we know that these two variables, when we are able to define them, when we are able to use behavioral equation to model them, then it means that at some point in time, these two variables might be the same, might be at state, or might be at equilibrium, might be a state of balance between the two. And that is what we call the equilibrium condition. And we have been seeing equilibrium condition over and over. Demand, we look at quantity demanded is equal to quantity supply. At this point, quantity demanded is equal to quantity supply is telling you that at this point, the individuals or the consumers agree on how much they want to purchase. And then the supplier also agree on how much they are going to supply in the market. So at this stage, the agreement has been done, and they are all in equilibrium state. Okay, so looking at these two variables, we say that for us to also connect two variables, it will come to a state that these two variables can also be an equilibrium state. And we can use so many equations to also define the equilibrium state of two variables. We have the quantity demanded and quantity to supply, which is very common. We have total revenue to be equal to total costs. If you are going to find the products, if you are going to find the optimal level of output, we also have the investment savings approach. When you are dealing with national income determination, and you are using the leakages and the leakage and injection approach, we are using savings is equal to investment. So these are, you can also look at total revenue is equal to total cost. These are all equations that demonstrate equilibrium condition of what? Two variables. Now we'll move on to what a functions are. What is a function? Please take note that what we are doing now, we are going through the basis of math. Get small basis, some of the fundamentals, so that we can use them to help us explain economic model when we go to the applications. Okay, like I said, if you have anything to say, just unmute yourself and talk, because when you raise your hand, I might not see your hand. What is a function? Function, we're saying that function is just a rule that try to assign a particular number to a variable. Okay, so it try to assign a real number or other integer, both positive and negative number, into a particular variable. For example, I have a function, so f of x or f of y. So I have f of q. I have f of q. I can say that this is a function of 2x. This is a function of 2x plus 5. This is my function. This is a function. Now, what the function does is that we are saying that for us to be able to know the magnitude of this particular variable, okay, then we can assign a real number, which is either integer or which is either positive and negative whole numbers, into the variable. Okay, so here should be my q. Here should be my q. Okay, this is a function. So for me to be able to determine the magnitude of this function, I can assign a number to the variable. So I can say where q is equal to 2. So if I say when q is equal to 2, it means that I'm assigning a number in each of the real numbers to each of the numbers that we have. Okay, so I'm assigning that q is equal to 2. So if q is equal to 2, then we can really find the function itself. So you can put where you see q, you put 2 there. Then this one must be equal to 2. Then you multiply here by what? 2. And that will give us 9. Okay, so this is the basic understanding of a variable. So a variable we are trying to assign a number to a particular real number that will help us estimate the real value of that particular function. And there are so many examples that you can think of. You get so many examples. Now, a typical example is when we have the consumption function. When we have the consumption function, then we can be able to illustrate that we can be able to distinguish clearly between this consumption function in terms of which one is the dependent variable and which one is the independent variable. So it's very clear that wherever we find ourselves in the function, we can be able to find the magnitude of the independent variable and then the magnitude of the dependent variable. Note that in typical cases, if you have a function of a number, let's say q, this is the same as y. This function is the same as y. It's the same as saying that you want to say y is equal to 2q. Y is equal to 2q plus 5. Okay, y is equal to 2q plus 5, where our y is the dependent variable and then our q is the independent variable. So it tells you that for q to increase, or changes in y depend on the value of what? Q. Okay, but changing in q does not depend on the value of y. So q become your independent variable, and then y become your dependent variable. So let's take note that the function here, we can see the differences in terms of the dependent variable and the independent variable. Okay. C is equal to 12.
Hello, doctor. Please,
C is
about
equal to
the
12.
function. Hello, doctor. Sir, please, about the function, can you re-echo the dependent and the independent variables at the function side quickly for me, please?
Hello.
Yes, sir.
Hello.
Hello, sir. Yes, sir. Please, can you hear me? Please, I was saying that,
Yes.
can you revisit the dependent and independent factors in the function for me? Function. Thank you.
Okay. Yeah. So let's use this one as an example. You will get to know the dependent and independent variable using the consumption function.
Okay. All right. Thank you, sir.
Yes. So this is a consumption function that try to link consumption to income. So these are two variables. We have the consumption and we have the income. Now, Keynes was trying to say that these two variables are closely related, okay, in terms of definitions, in terms of behavioral actions. Okay, so he was trying to say that he was trying to do a study to see if what is the relationship between these two variables, income and consumption. And he found that when your income increases, your consumption also increase. So he found that there is a positive relationship between these two variables. Now, which of them is your independent variable, and which of them is the dependent variable here in the consumption function? So we can clearly see that your consumption depends on how much money you have in your pocket, how much you spend on goods and services, how much you spend on other utilities, how much you are going to spend with your family, your household. Your consumption is only possible if you have some level of income. Okay, so your consumption become your dependent variable, and then the income become your what? Your independent variable. Now, first, let's look at within the model and see which of the variable is being determined within the model. We can clearly see that within this model, we are having only two variables, that is consumption and what? Income. And then we stated that consumption is dependent on income within the model. Within this model, consumption depends on income. So we say that your consumption is your dependent variable. Now, look at the income. Why do we say income is independent? We said that within these two models, you cannot find any variable that income depends on. So income is standing alone, it is independent. But if you go outside the model, you can realize that there are other factors that affect our income, but they are not in the model. So we say that the income is your independent variable that is being determined outside the model. So from this consumption function, we can clearly see that our independent variable is income, and then our consumption is our dependent variable. Now, if you want to know the level of consumption, then you should know how much income you have. If you want to know the level of consumption, how much you are going to consume, then you should know a magnitude, how much income you have. So if you assume that your Y, which is your income, is equal to 100 Ghana cedis, 100 Ghana cedis, then it will determine how much you are going to consume. So you can substitute the 100 Ghana cedis into the consumption function, then you can find the value, how much you are going to consume at the end of the day. Okay, now we've seen two things here. We are seeing two things here. Let me just highlight on them, even though you might have gone through that, but let me highlight the two things here. Okay, so let's see this. We have 12 here, and we have 0.3 here. What does it? What are they for? What are they? What did they stand for? I believe you have ever gone through consumption function before, so you should be able to tell me what the 12 stand for and what the
Master,
yes.
please, the 12 stands for a constant,
Okay.
whilst the 0.3 is a coefficient because it is related to a variable y, so it is a coefficient.
It's a coefficient. Okay.
Yes, yes, please.
Yes. So mathematically you are correct. That's good.
Okay.
So who else? Who else want to say something? What does the 12 stand for? And what does the 0.2 stand for, 0.3 stand for? Okay. So like my brother said, the 12 here is your constant, or sometimes in mathematics you call it intercept. And then the 0.3 is your slope. Is your slope. But you go beyond that when we talk about economics. In economics, the 12 here is what we call the autonomous consumption. I believe you've heard it before. Autonomous consumption. And it is a consumption that do not depend on your income. Okay. So we've seen that, first of all, we realize that your consumption depends on income. Okay. It means that there are some times that even if you don't have income, you still have to consume. So we call it autonomous consumption. So when your income is zero, then your consumption will be 12. And we call it autonomous consumption in economics. Now, what is the 0.3 here? The 0.3 here in math, we call it slope. It determines the steepness of the curve, whether the curve if we plot this one, whether it is downward sloping or upward sloping. Okay. But in economy, we call it the marginal propensity to consume, MPC. We call it MPC, marginal propensity to consume. And I believe you have done this in your principle of economics. MPC. Now, what does this MPC stand for? Okay. You see, if we are saying that if your income increases, we expect your consumption level to also increase. But by what magnitude? Okay. So the marginal propensity to consume try to explain the fraction of your income that you spend on consumption. The fraction of income that you spend on consumption. Remember that if, let's assume that if your income increases by 1 cedi, if your income increases by 1 cedi, mostly you don't spend all the 1 cedi on consumption. You will spend a fraction of your 1 cedi on consumption, and then the rest you have to save it. So out of one, we are saying that the marginal propensity to consume is the fraction of income that a consumer spends on consumption. So here the 0.3 means that you are spending 30% of your income on consumption. 30% of income on consumption, and the rest you have to save it. So here we are able to distinguish between the two variables, the dependent variable and then the independent variable, and how these are related. These two variables are related. Okay, so the one who asked the question, I saw you are now okay.
Yes, sir.
Okay.
Yes, sir. But I was trying to find out, you see, the functions, it comes with f of x or f of something. So that was where I wanted to know.
Okay.
Which one was the dependent and which one was the independent. But
Okay.
I'm okay.
Okay.
Thank you, sir.
Yeah. So if you are given the value of y, you can find your consumption. You can find your consumption. If you are given the value of y, you can get substitute the value of y, then you calculate it to find the how much you have. So it also means that if you are given consumption, you can also find the value of, if you are given the dependent variable, you can also find your independent variable using the same approach. Okay. So if for here, we said that, example here, we said when your y is equal to 90, when your y is equal to 90, y is equal to 90, it means that you can substitute y into the equation. So we are going to have c, we are going to have c to be equal to 12, 12 plus 0.3, then multiply by 90. Multiply by 90. So if we do this one, we are going to get 39. 39. So it tells you that when you have 90 Ghana cedis, this is how much you are going to consume. You are going to consume 39 units of the commodity. Okay. So it is also possible that you can be given your consumption, your dependent variable, and you ask to find your independent variable here. So if you assume that, your consumption is equal to 39, if your consumption is 39, you can find the value of what? Y. Can you quickly do that for me? If your consumption is 39, what would be your value of income?
So it's 90. So
How is it 90? Did you still working?
yes, sir.
Okay.
So for this one, you group lighten. So you take the 12 to the other side, and then the 12 is positive. When it crosses, become negative. So
Okay.
39 minus 12 will give you 27, and then 27. So this one, we have to make the y the subject. So we divide both sides by 0.3, and then 27 divided by 0.3 give us 90.
Okay, that's fine. Yes, so I intentionally brought the 39 here because we are finding the consumption here and it was 39. And because we use the 90, the y is equal to 90, that is why we are getting the 90. So you are right. Okay, so that is how we can manipulate these two function away. So let's look at the various forms of function. There are various forms of function that we are going to look at. We have the monomial functions. These are the simplest form of functions that consist of only one term. Only one term. And their degree of of power or exponent. So when we talk about the mono means one, and then we are saying that the monomial functions are just the simpler function that consists of only one term. Only one term. So if you have a function f of x is equal to let's say 3x squared. This is a monomial function because it comprises only one term. Mono, one, means one. Okay. Now, this function like this is the independent variable. Sorry, this is the dependent variable. The f of x is the dependent variable. And therefore, we can replace this one by y. So you can define this function as y to be equal to 3x squared. Now, we are bringing the fx here to signify that we can assign x to a number so that we can substitute that x to the function and get the value of y. That is why we are putting the f of x there. Okay. Now, we are also saying that a function that have more than one term or that has more than one monomial terms, then we call it a polynomial function. A polynomial function. So the polynomial function, we can find. So for the polynomial function, we have more than one term. So one more than monomial function will give us the polynomial function. So from the example here, we have the f of g to be equal to the first term, the second term, and then the third term. So these are three more than one term. So we call it a polynomial function. We also have to note that if a function have only the degree of 2, we all know that it is what we call the quadratic function. So with the quadratic function, it comprises, the degree is 2. The polynomial can be a combination, and the monomial can be the degree will also determine with only one term. Okay. So with the monomial function that we have the degree of monomial, and then we also have the polynomial we also have the degree that determine the level of polynomial that we have. Then we'll come to the quadratic. We know that the quadratic is also square. The higher degree in quadratic equation is 2. But the higher degree in polynomial equation is n. The n here can be any number. Okay. And then the higher degree in the monomial function is also n. The n can be also different, any number. So in simple, we are saying that with the monomial function, we are dealing with only one term, with a degree. Then the polynomial, we are dealing with more than one term with the polynomial what degree. And we also have the quadratic function, which also deal with more than one term with a degree of what? 2. So these are some of the functions. We have type of functions. We have the form of function. The form of function are 3. We have the monomial function, we have the polynomial function, and we can also have quadratic function. These are all the forms of functions. Now we also have type of functions. The first type of function is what we call the algebraic function. Now, when we talk about the algebraic function, we are talking about a function that describes a root as a polynomial function or equation. Okay, so we have a polynomial function. We said that the polynomial function consists of more, it has more than one term. For example, if I have 3x squared plus 20x plus 5, this is a polynomial function. Sorry, let me add 3 here. Let me put 3 here. And let me put 2 here. And let me put x here. Okay. This is a polynomial function. This one is a polynomial function. Now, so when we are talking about algebraic function, then we are taking the square root of the polynomial function. The square root of the polynomial function. So polynomial function or the algebraic function are expressed as a root of the polynomial equations. So if I now write this one as a function, if I now bring a function, the root symbol here, then we are talking about a quadratic algebraic function. So algebraic functions are expressed in polynomial forms. So expressing the polynomial form in terms of the root, then we talk about the algebraic function. We also have the exponential function. Now, with the exponential function, the independent variable appears in the exponent. The independent variable appears on the exponent. So we can have y to be equal to, let's say, 5x, 5 raised to the power x. Okay. Now here, the y is your dependent variable, x is your independent variable. And then your 5 is a constant. Okay. So this is what we call the exponential function. So anytime you see an exponent, a function that have a power being the independent variable, then we said that function is an exponent. So that there's a difference between exponent and power. Exponent and power. With the power the exponent is raised to the power a constant. The exponent is raised to the power a constant, not an independent variable. Okay. So with the power function, we may have y to be equal to x raised to the power b, where b is a constant. Where b is a constant. So to translate this one, you can say y is equal to x raised to the power 5. Raised to the power 5. So this is what we call a power function. And this is what we call the exponential function. To take the note of the difference. With the exponential function, the exponent is in the independent variable. But with the power function, the exponent is a constant. These are the two different variables we can talk about. Two different functions that we can talk about. And we can also look at rational function. when we talk about rational function, we are also talking, it's being defined by fractions. Okay, so we have a fraction that contains two quadratics or a mixture of polynomial and quadratic forms. So expression polynomial forms in terms of fractions, then we call them a rational function. A rational function. So a rational function expresses polynomial function or quadratic function into a fraction. And we have seen the examples there. We have seen the examples clearly there that this is a rational function. We try to put quadratic equation into a fraction form. So we call it a rational functions. Then we have the power function. I have explained the power function already, so I don't have to go there again. So we have the inverse function. So with the inverse function, we interchange the independent variable with the dependent variable. So this is just simple and straightforward. So we are taking the inverse. So if you were defining y to be a function of x, then we can say that, or if we were defining a function, let's say f as a function of x to be equal to y, with the inverse function, you are going to say that f of y is equal to x. You are just interchanging the position of the independent and the dependent variable. That is all. So with the inverse function, you are just taking the inverse in terms of the two variables. Then we can also talk about the explicit function. Now with the explicit function, we are saying that it is a function in which the dependent variable can be written explicitly in terms of the independent variable. So here we can clearly, when you define the explicit function, we can clearly see the distance between the independent variable and the dependent variable. We can clearly see the differences. That the dependent variable is a function of the independent variable. So we can clearly see that with the explicit function. It is explicitly what? Stated. For example, the consumption function. Where's my marker? Let's use the consumption function, for example. So the consumption function, we are having C to be equal to 12 plus 0.3 y. Now, this is what we call an explicit function because it clearly states that consumption is a function of income. Clearly, it has stated that. That is what we call the explicit function. Now, we also have what we call the implicit function. Now, with the implicit function, you will find it difficult to distinguish between the independent variable and the dependent variable. You cannot differentiate them. Now, here, the explicit function uses this equal sign to differentiate between the independent variable and the dependent variable. But with the implicit function, you will not find anything like that. So with the implicit function, the dependent variable is not defined as a function of the independent variable. So let's look for example of the implicit function. I'm going to use the same thing. We are going to, if you have C minus 12 plus 0.3 y is equal to 0. Now, from here, how will you determine that this one is a dependent variable, this one is an independent variable? So it becomes very difficult for us to determine that because they are all in one side, one equation. They are all in one side. So it becomes very difficult for you to identify that consumption is a function of what? Income. And this is what we call the implicit function. The implicit function. But with the explicit function, you can clearly see the differences. We can clearly see that consumption is a function of income by the equal sign here. By the equal sign. But with the implicit function, you cannot find anything like that. Okay. Okay. So let's move on to, we are still on the type of function. We look at, yeah, this is the implicit function that we spoke of. We can also look at the logarithm function. The logarithm function are a direct opposite of the exponential function. Remember that we talk about the exponential function. We said with the exponential function, the independent variable is the exponent. The independent variable is the exponent. And with the power function, the exponent is a constant. The exponent is a constant. Okay. So here we can clearly see that when a variable is expressed as a function of the logarithm of another function, then that function is also defined as a logarithm function. So the logarithm functions are a direct opposite of the exponential function. So if you have this, if you have y is equal to the log b base b x bx. So this one is telling you that we are going to have, if you want to find the exponential form here, you are going to have y, let me write my pen. Okay, so here, let me raise my pen. You can express this one as a exponential form by putting it as y b raised to the power x. Okay, raised to the power x. So this is a logarithm function, which is a direct opposite of the exponential function. Now, with the exponential function, the independent variable is the exponent. Okay, but the logarithm is the opposite. So the logarithm here, we rather express the independent variable as a function of the dependent variable, and it's raised to the power constant. Okay, so these are all logarithm functions. We'll go into each of them, especially the logarithm function. We'll be doing more on logarithm. So when we get there, we'll get to know all these things about logarithms. Then the classes of economic model, I think we have already explained this, that I use the models and then the theories to try to explain that economic models consist of a set of ideologies, they consist of a set of ideas, okay, that try to explain an economic phenomena. But that's the economic theories, okay. We call it theoretical models. The ideologies, the principles, the assumptions that try to explain a particular phenomena. That's what we call the theoretical models. Now, the empirical models is the same as the economic models. The empirical model try to represent these theoretical models into a formal way. So it's a formal representation of the ideologies from the theories. So with the empirical model, we can use equations, we can use data, we can use equations and data to represent the ideologies, to represent the assumptions, to represent the principles from the theories. Okay, so it's a thing that we can verify, thing that have implication in economic behavior, that we can use the theories and empirical model to answer these questions. So when we talk about the two main classes of model, we are talking about the empirical model, and then the theoretical model. The theoretical model, it's about the principle, it is about the assumptions, it is about the ideology that a particular model comes in the form of ideas from some people. Okay. Now the empirical model try to now translate these ideologies into equations or into a formal representative, and then that will simplify how we can simplify the complexity of the theory. So some of the theories, some of the ideologies, some of the principles that we have, some of the assumptions that come with the theories are too complex, very complex, that we cannot comprehend. So what we will do is that we use the empirical models that try to simplify this by putting it in a simple representation, by using simple equation to do that. We can look at some of the theories that we have, a lot of theory that we have. We have the rational choice theory. These are ideologies, these are assumptions, these are principles from some people. We have the rational expectation theory, we have the principal agent theory, we have the theory of optimal taxations, we have the resource curse theory or the dark disease theory, we have the Laffer curve, we have the solo model growth mode theory. These are all theories. These are all theories that come with their own ideology, come with their own principle, come with their own assumptions. So we can always use empirical studies. The empirical tries to simplify this complex theory into simple form for us to be understand. Okay, so if you look at the dark disease, the resource curse disease or the dark disease, it is a theory that macroeconomics, I can't remember vividly the name of the person, the one who proposed the theory. He said that when a country discover a natural resources, that country seems to forget about the other sectors or other important sectors within the economy that move the economy forward. So you discover oil and you forget about agric, you forget about the sector, you forget about the mining. Sorry, the mining, and all what you are doing is to concentrate on the oil and collapse the other factor or the other sectors. Okay, and then that is the theory that the dark disease is talking about. And it was in Africa here, they use Nigeria as a typical example. When Nigeria first discovered their oil, they ignore the other functional factors of their economy, especially agri. They ignore the importance of agri. So they were on the oil every day oil. All their resources were channeled to oil, leaving the vital part of other sectors. And that had a detrimental impact on their economy. People were suffering, they were not producing, they were shortage of apples. So their inflation, their economy was being at state of dismay. And that means that it was causing a lot to them because of this ignorance about other sectors while concentrating on oil. So all their resources were channeled to oil, leaving the other sector. And that has impact on them. This is our ideology. This is an ideology. So we can use empirical studies, we can use data, we can use equations to represent this one in formal way. So the theory can be represented in the formal way by using what? The empirical model. So the empirical model here, like I said here, it tries to model the theories using mathematical equations, using verifiable data, using predictions, okay, to what? Try to model whatever theories are coming to say, so that it will make the complex theories simple for us to understand and relate to. Okay. So there are other example of a theory that we can look at, and how the empirical model try to explain that. For example, we have this theory, the theoretical model of consumption behavior. Like I explained earlier on, that John Maynard Keynes in the 1937 tried to model the behavior of individuals in terms of how much they consume and how much they spend. Okay, so he found that there's a link between consumption and income. So when your income increases, your consumption also increases. This was the idea. This was the theory. This was the theoretical model that Keynes came up with. Okay, now the empirical model comes to play if we try to represent this ideology into an equation. So the equation will help us simplify the theory by using the equations. So if you use the equation, you clearly understand the dynamics. You clearly understand that we can find the magnitude of consumption when income is increasing. You can find the magnitude of income when your consumption at a certain level of consumption. What would be your income? So we use empirical to simplify this model. Even though Kay has stated a theory, its idea well, we can use the equations, we can use the empirical to also translate this one into a simple form for understanding. So they are very useful. Theories and empirical studies are very useful in everything we do, especially those of you who want to go into research. We are going into research. We have a section that you have to model. You have something we call the theoretical models, where you come out with the theories that support the theory that are supporting your study, that are behind whatever you are studying. So then you have a section that you translate this theory into empirical model. So we have the theoretical model aspect and then the empirical model. The empirical model will now come and try to put the model that the theoretical model into an equation for you to now use data to find whatever relationship you are finding out. So these two concepts are very important that we have to understand them. Yes, I will not talk much here again because we spoke about a variable. I have defined a variable already, so there's no need for me to go through it. But we can look at other simple things. We know what exogenous variables and endogenous variables are, but what we do not know is a constant. What is a constant? When we say a constant is a variable that, or it gets a direct opposite of variable. Constant, it doesn't change. Something that is constant, something that doesn't change over time. Okay, it's what we call a constant. Okay, guess not like a variable that we said that a variable can change over time. It can change in magnitude or in kind. With a constant, it is stable. It does not change over time. Now, what is a coefficient or a parameter? Now, parameters are coefficient or coefficient when a constant is attached to a variable, then we call it a parameter or a coefficient. For example, we know what a constant is. We know what a constant is. Where's my pen? We said a constant is any thing that does not changes over time. So we can say if you have 20, 20 is a constant, 40 is a constant, 50 is a constant. These are all constant. But if we have something like x can be any number. X can be 1, X can be 2, X can be 3, X can be any number. So we call it a variable because it changes in number in terms of magnitude. Now we are saying that a parameter or a coefficient is when you attach a variable to a constant. A variable to a constant. A variable to a constant. Here, so this is our constant. Let's say 20. Where's our variable is x, this is x. Okay, so it means that this one become a coefficient or a parameter. So mostly we use symbols rather than numerical variables. So we say symbol, we can use alpha, you can use beta, you can use sigma, and the rest. These are all symbols. Okay, so if you have 20 alpha or 0.2 beta, so this one become your parameter or your coefficient. Okay, you can even have x, alpha x, so alpha x or alpha p. This is a parameter or this is a coefficient. Okay. So basically we are saying that we will talk about the coefficient or the parameter when a variable and a constant come together, then they form the parameter or the coefficient. So a typical example, we've been using the consumption function now very well. So let me write this one and then ask some few questions. C is equal to 12 plus 0.3y. 0.3y. Now here we can identify all what we spoke about. We can identify the independent variable, we can identify the dependent variable, we can identify our constant, we can identify our coefficient or parameter. So what is our dependent variable? We know that it is our C. Our 12 is our constant, something that does not change. Our Y is our what? Our independent variable. Then this one will give us our parameter or coefficient. So we can identify everything in this equation using the variable that we defined earlier. Okay. Now, sometimes instead of using values, we can sometimes use parameters. Just like what we have here. C is equal to alpha plus beta y. This one become our constant. This one will become our parameter or our coefficient here. This one will become our independent variable, and this one become our dependent variable. Okay. So instead of using function, we can use our parameter to also define that. Okay. So the first unit of unit 1 is done. The first unit of unit 1 is done. If you have questions on what we have done already, you can ask before we move on.
Sir,
Yes.
please, I would like to know if the consumption function here is the standard consumption function that we'll be using, or is
Oh, it might change this for this for the purpose of this lecture. We might be using that consumption function, but it is not standard change.
all right, sir.
Your consumption pattern might be different from another person's consumption function. So it is not constant. Because we said that consumption and income are related. Okay. So when your income rises, your consumption, much income you have might be different from the income that you also have. So the consumption function behave differently depending on the individual involved.
All right, thank you, sir.
All right. Any question before we move on? What time would you like to go for the break? First rep.
Sir,
What time will you like to go for the break?
sir, it will depend on the content that we are to treat for today. So if you think we are in the middle of the content, or we've taken half and it's left with half, I think we can get the break.
No, it's not about the content. It's early morning, so maybe you want to go and take some breakfast or something before you come back. Let's go on break 9:30 or 10 o'clock or something.
Okay, sir, I think let's make it 9:30.
Okay. All right. So let's continue. If there's no other concern, let's now proceed to the other unit of the first unit. Okay. So this is self-assessment. So you can just sit down, take your pen, and try to solve these simple equations. Okay, so try to go through it yourself. These ones are not anything difficult. We just want you to practice some of the things that you have done already. So here, you are just multiplying this one by this, multiplying the same thing by this. Then you add it, then you come and multiply this one by this, and then multiply the same thing by this. Okay. So it's not anything difficult here. So when you go, try to solve it yourself and then see how we are going to get. Then when these equations here, this one, you can use the elimination or substitution method to also find these equations. Okay. Then this is demand, and this is demand equation. You know how to find them. Just equate them and find the value of X and Y. P and the QD or QS. Okay. So this one become equation 1, equation 2, and equation 3. So here we are having 3 equations with 3 unknown. So you use the simultaneous, or you use the substitution approach to find the value of x1, x2, x3. So you can try them later on, and when you are finding anything, you can let me know. Okay, so now let's move to the next unit. We are going to look at first, we are going to look at the basis. Did you say we are doing the 4 hours today, right now, or we are doing 2 hours?
So it
What's
was 4 hours, sir.
okay? So now let's go to now pick them different, and then go deep into that. The first one is indices. So we are going to look at what indices. It will come to logarithm and the rest. So what is the cost outline for the indices? We are going to look at the indices, logarithm, and root and radicals. So the first one is indices. Now, indices are very important part of mathematics. It is the heart of mathematics that at least everybody doing basic mathematics should understand this. Or else, if they ask you to multiply 5,000 times, and you don't know indices, you don't know what indices are, you may try to multiply 5 by 5 by 5,000 times. By finished 1,000 times, that would be too complex for you. Okay, so if you are ignorant about indices, you may try to do this multiplication till 1,000 times, and someone with the knowledge of indices will get you simple approach to get the answer. So for us to solve this complexity, indices has come to help us know that we can use the power or the index or the exponent to clearly represent any complex multiplication. Okay, and the example is that if you have to multiply this one by 1,000 times, you can just put it in a simple way, then you go away. So if we have xn raised to the power x raised to the power n, it means that we are going to multiply x by x up to n times, up to the number of n that you have. So if n is equal to 2, so if n is equal to 2, then you are going to say it's going to give you x multiplied by x, and you are good to go. Okay, and thankfully they have incorporated this into calculator that you can simply do it. You can simply do the calculations there. So indices before then has really come to help us a lot. If not, we're trying to explain or trying to solve a lot of problems by using complex way. So if you have x raised to the power n, where n is equal to 5, so it means that you are going to multiply x by x by x by x 5 times. That is the simple thing that we are going to do. For example, you have, let's say, 5 raised to the power 3, and you want to find the value of this. You are just multiplying 5 by 5 by 5 3 times, and that will give you the answer. That will give you the answer. So this is the simple illustration of what indices. And in our core maths, we used to do this one. So a raised to the power 1 is equal to a. Then a raised to the power 2 is it tells you that you are going to multiply a by a. Then when you come to a raised to the power 3, it means that you are going to multiply a by a 3 times. And when a is equal to a raised to the power n, it means that you are going to multiply a by a n times. And that is all about indices. So we'll move to look at the laws of indices. The laws of indices. The first law of indices is the multiplicative or the multiplication law. And the multiplication law states that if you have two functions of the same base, and you are multiplying them, then you add the exponent. So here we can see that here is base A, here is base A. So when the base are equal and you are multiplying them, you get add the exponent. And that is all about the law of indices under the multiplication law or the multiplicative law. The multiplicative law. Okay, so the first example, if you have 3 raised to the power x plus 3 raised to the power x or 2x, it means that when the bases are equal, you can say that you are going to have x 3 raised to the power x plus 2x plus 2x. There's a lot of examples. These are the examples that you can look at. So the first one is 2 raised to the power 2, 2 raised to the power 3. So when the base are equal, you get add the exponent. So you are going to get 2 raised to the power 5. Okay, so here you are going to get 2 raised to the power 2. Here we are going to get 2 raised to the power 1. Because here, any number raised to the power 0 is 1. So here is the same as 1, right? So any number raised to the power 0 is 1. So you can represent this one and then find the exponent. Okay. Now, it means that anytime the bases are not equal, then you cannot add the exponent. You cannot. Anytime the bases are not equal, then we cannot add the exponent. Okay. But assume that you have, if you have, let's say 9, sorry, this is multiply. If you had 9 multiplied by 3 raised to the power 2. No, this 3 raised to the power 4. 3 raised to the power 4. How will you go about this? What will you get? Are the bases equal?
No, sir.
So how do you find how do you make this base to be equal?
So this one you break the 9 down.
Yes. So break the 9 down. How do you break the 9 down?
You get 3 raised to the power 2.
3 raised to the power 2.
Yeah.
Multiplied by 3 raised to the power 4. Okay. Then you can now add the exponent to be 3 raised to the power 6. Okay. Now, what this one is telling you is that maybe we are saying that in typical questions, you might not be seeing these things easy like that. We might give you a complex number that you have to find the exponent. You have to make sure that the bases are equal first before you can apply the first law. So take note that there are some situations that will make it difficult. We make the exponent very complex, and you have to be able to break it down and then find the value of what, and find the using the law to now find it. Okay.
Sir, please, a situation whereby we cannot break the number down to what will we do?
A situation where you cannot break it, then you cannot multiply, you cannot add them. So you just leave it like that. Okay. So it means that you can also be giving, for example, let me use the same example. I have this 9 and I have 2x plus, let me say, 4. And this one, I'm multiplying this one by 3 raised to the power, let's say, 10. and they ask you to find the value of x. Who can do this? Can you do it?
Yes, please.
Yes, please.
Yes. So let's try it. Everybody should try, and then let me get what. Let me see what you have gotten.
Hello, sir.
Yes, sir.
I had 3 or 4x plus 18.
Three over 4x plus 18.
No, 3 power 4x plus 18.
3 power 4x plus 18.
Yeah, that's what I had.
It's half.
One over 3. 3 is 4x plus 18.
No.
Yeah.
Hello. I have x is equal to 8.
You have
X is equal to 8.
8. Okay. Yes, who else?
Okay, please, you are coming.
Auxilia coming. And then
Let's see.
Yeah, x is equal to 4.
S is equal to 4.
Yes, please. That's what I got. X is equal to 4.
Okay.
Listen, I had 3 exponents, 4x plus 18.
3 exponent
4x plus
4x
18.
plus 18.
Yes,
Okay.
please.
So here you are going to get 3. Then you multiply here
Then
by
I also had s equal to 4.5.
2x. Okay. Plus 4. Then
Sir.
plus
Hello.
10.
I mean,
Yes.
So are we to leave it in base form, or we have to solve or equate it to 0? Which one? Which one are you doing?
Oh, your line is breaking. I can't get you.
I said, are we to leave it in a base form or we are to equate it and solve and find the x?
There's no, okay, so I said you should find the value of x, or did I ask you to find the value of x?
Yes, sir.
Okay. Okay, so let's see.
The x is equal to minus 4.5.
Okay, so let's see
if
if
x is equal to 4.5.
Okay, so this one you can expand it.
Yeah.
If you expand this one, you are going to get 4x plus 8, then plus 10.
Yeah.
Plus 10. So
Yeah.
4x plus what? 18.
Yeah.
So here you are going to get 2x. 4 can go to 18, eh?
Yes, sir. 4.5.
Okay. Or you can even break it further. 2x plus 9. 2x plus 9. Okay. Now, if I ask you to find the value of x, then that one, if you equate this one to 0 and find the value of x, we are not right. We are not wrong.
Yes, sir.
But
Yes, sir. Okay.
if I ask you to solve it, it
Mhm.
means that you are supposed to leave it this way. You are supposed to put 3 raised to the power 2x plus 9 this way. If I ask you to solve it without finding the value of x, this is what you are supposed to get. But if I ask you to find the value of x, if I ask you to find the value of x, you will not equate this one to 0, and then you make x the subject.
Yeah. Okay.
Yeah. So that's the idea about it.
So, sir, please, why is it that? Why didn't we leave the answer in 4x plus 18? 4x plus 18.
4x.
Why did we break
plus,
it down to 2x? 4x plus 18. So why did we break it down
to
2x plus 9?
2x
plus 9.
Just to make it in the just to keep it in the simplest form.
Okay.
Yeah, it's not anything. Even you can leave it that way as you like. But you see, when we are preparing, when there's a marking scheme for these things, we always leave the answer in the finals form. So you leave this one, you might get your marks, but the final form will also be there, maybe 0.5 marks there too. So always leave your answers to the final form or the simplest form. Okay. Now the second law of indices is the quotient or the division law. Now the division law states that when you are dividing two terms with the same base, then you subtract the exponent. You subtract the exponent. So this is, you are dividing a raised to the power m by a raised to the power n. Because a and a from the bases are the same, you will subtract the exponent. So the difference between the division and the quotient law and then the multiplicative law is that with the multiplicative law, we are multiplying. So when you are multiplying, you are adding. But here you are dividing. When you are dividing and the base are equal, you are subtracting. Okay. So here too, the same strategy. It means that when you are giving any function or when you are giving any number to work, you need to always break it down first before you can divide. Before you can divide them. So Example, if you have if you have 9 divided by 3 raised to the power 2, we are dividing these two things. But we realize that these two things are not the same for the first stage. So it means that you have to break them first, make the base equal before you can do the division. So here you are going to get 3 raised to the power 2 dividing 3 raised to the power 2. And because the bases are equal, when you are dividing, you are going to subtract. So 3 raised to the power 2 divided by 3 raised to the power 2 is going to give you 3 raised to the power 2 minus 2. 2 minus 2. That is 3 raised to the power 0. And your answer will be what?
1.
What will be? Yeah, it will be 1.
1.
Okay.
Yeah.
Yes. So here again, it's just about trying to make the bases equal, then try to do the division, then subtraction. Now here again, if you given a function that the bases are not equal, then you cannot do anything about it. Just leave it as it is. You don't try to subtract it or don't try to manipulate anything. If they give you 210 that they are not equal, please, you cannot subtract it. You cannot subtract. And then take note that if we are also giving you, take note that we said when you are dividing and the bases are equal, subtract the exponent. It's not the same as when you are subtracting and the bases are equal. What will you do here? What should we do? You have 5 raised to the power 3 minus 5 raised to the power 2. What will you do? Do you have anything to do here?
Yeah, here what you divide?
Huh? Do you have anything to do here? Absolutely, we don't have anything to do here. I hope you can hear me.
So we can hear you.
Yes, sir.
Yes, Doc, we
Yes,
can hear you.
Please.
Okay. Okay. So what I'm trying to say is that when you have something like this, it's not the same as having the division sign. It's not the same. These are two different things. Remember, the law emphasizes on the division, not subtraction. So please don't say that because we are subtracting, you will come and divide them. No, that is not how the law is saying. The law is saying when you are dividing, you subtract. The law is not saying that when you are subtracting, you divide. No. So take note. Okay. Now, the second law of division is the power law. Is the power law. Okay. With the power law, we are saying that when you are multiplying, so when you are multiplying a function that is also outside the function, then you guys have to multiply the number inside. So here, it gets pretty simple. You are having A, and A is raised to power M. And then you move. That's all. So you are going to get Mn. That is the power what? Rule. That is the power rule. You get like having 3 raised to power 2, and the whole of this one is raised to the power 5. So what simply this one will mean is that you are going to have 3 raised to the power 2 multiplied by 5. I hope this is also simple and clear.
Yes, sir.
Okay. Then we can move to another law, the zero power law. The zero power law. Now, the zero power law is also saying this one there is something that we all know, that any number raised to the power 0 is 1. I will find one day to try to prove this, how this is proof that any number raised to the power 0 is 1. Okay, but for now, let's take it as it is, as a rule, that even if you have, I think there's a proof, even if you have 2,000 and it's raised to the power 0, it's going to give you 1. Going to give you 1. Okay. Now, yeah, so now it means that we can combine 2 or more laws to get another law. Okay. So looking at the division law, like we stated earlier, I gave example. The division law the example that I gave earlier on. You have 3 raised to the power 2, and then 3 raised to the power 2. You are dividing them. The base are equal. So you are supposed to subtract 3 raised to the power 2 minus 2. And that will give you 3 raised to the power what? 0. And this one will lead to another law, which says that any number raised to the power 0 is 1. Okay, so one law has led to another law. Okay. Now, we can now move to the...
Sir,
You have a... Yes.
I think it's now 42.
Okay, so we can go for a break and come in. Yes,
Yes.
so we come at... I think coming back at 10 will be fine.
Yes, sir.
All right. Would it be enough for you?
Yes, sir.
Yes, please. Yes, please.
Okay, so let's come back at 10.
Okay.
All right, thank you.
No, let's go and
Sure.
come. Let's go and come.
Are we on break? Are we on break?
Hello.
Hello, sir.
Lawrence.
Sir. Hello. Hello, sir.
Uh-huh. I thought we say we'll come back at 10.
Yes, sir.
No, people don't want to come back.
So we are back.
Okay. If you are back, then we can proceed. Okay. So let's move to the fifth law of indices, fixed state, which talks about we talk about the inverse. Talk about the inverse or reciprocal. So it means that we can always convert negative powers into a positive powers when we are dealing with indices. So when you have an indices that is raised to the power or have an exponent to be negative, we can always reverse it to positive powers by taking the inverse of it. Okay, so a typical case is given there where we have a raised to power minus n. Okay, so this exponent is negative. Okay, so to take the inverse or to make this positive, then we take the reciprocal of this. That is, for us to make this one to be positive, then we have to put the inverse. And the inverse, remember that if you have A is always over 1. Okay, so if we want to take the inverse of this A, it's going to be immediately 1, that's the inverse. So it becomes 1 over A. 1 over A. Okay, so if we want to take the reciprocal of this, it means that we are going to have 1 over AN. This time around, because you are inversing it, the negative sign here will turn into positive. Okay, so the fifth law of indices is about converting negative fraction or negative powers into positive powers using the inverse or the reciprocal. So whenever you are given a function that is negative or a power function that is negative, you can always convert it to a positive powers. An example is given down there where we have a raised to the power minus 3. Okay, the exponent here is minus, but I want to keep it, want to put it as a positive function, positive exponent. So we'll just take the reciprocal of this. That would be 1 over a raised to the power 3. A raised to the power 3. So this is the reciprocal that we are talking about. So anytime you are giving a number, please, that is the power is negative, you can always convert it to a positive using the 5th law of what? Indices. So if you are giving, let's say, 2 to the power negative 2, okay, you can always write this one as 1 over 2 raised to the power 2, positive. So we have turned the negative here to positive. Okay. I hope this law is also clear.
Yes, it is, sir.
Okay. Then we'll move to the law. The 6th law is also one typical a number. So again, you are having a 1 over n. 1 over n. So you can one serve as the square root. The square root, depending on the number that you have. Depending on the number that you have. Okay. So if you have this one can represent the square root. So this one, you can rewrite this one as the square root of a. The square root of a. Then this n here will come out to this place. Will come out to this place. So you have 3 raised to the power 1 over 2. So it means that you are going to take the square root of 3. Then the 2 will come here. Again, you have 3 raised to the power 1 over, no, let's say 5 raised to the power 1 over x. It is telling you that you can rewrite this one as the square root of 5, then the x will come here. Okay. So this is how we are also going to represent this in the law of indices. When you are given this function, we can convert it into the quadratic form or into the root form. Now, another one under this is when you are given another one under this is, let me clean this. If you want to say something, just raise your hand and say. If you raise your hand, I might not see you. So this one.
Okay, sir, please, my hand is up.
Go ahead.
What if the numerator is greater than 1? A function is given and the numerator is greater than 1.
Yes, so we are coming to that. Okay. So the next thing we are going to look at is when you have a m raised to the power n. Right now, here we know the position of the n already. What is the position of the m? Okay, what is the position of the m? So if you have something like that, we can always convert this one to in the form of, so we can convert this one in the form of 1 over a, sorry. We will convert this one in the form of we can convert this one in the form of a 1 over n. So we can always convert this form into this. So the m is there, so it means that we can multiply this one by m. It's the same thing. So it means that if you multiply this m by this, we are getting back to this. We are getting back to this. So we can always do this. You can always do this. Okay. So when you are able to convert it to this, then you can now put it in the form that you want. So let me restate that. So let me restate that. If you have a m over n, it's the same as a 1 over n multiplied by m. It's the same thing. This one and this one, there's no difference. This one, when you multiply the m by this, the m is going to play the 1, so you get the same as this. Okay. And you know how to represent this. This one alone is going to give you the square root of a. Then you bring the n here. N here. But remember that the whole of this one is multiplied by m. So you can just put a bracket here. Then you put the m there. That is all about this. So like you ask your question that if n is greater than, if 1 is greater than, you have a number that is greater than 1, this is how you are going to represent it. Okay, so if you have, let's say 16 to the power 3 over 2. 3 over 2. Okay. This n here, you can rewrite this one as 16 1 over 2. And this one is representing multiplying by 3. Because if you multiply by this one by 3, it will come and affect the 3 here. So when you have something like this, then you don't have to bring the bracket there. Sorry, I'm coming. Let me just erase this. And then I can't be typical to this. So this one is multiplying by this. So you multiply by this one by this one. Then you get back to this. Okay. So when you get something like this, then you can now replace it. You can now put it in the root form. So you are going to get the square root of 16. And we know that our 2 will come here. And then you multiply here by what? 3. 3. So this is how you are also representing these situations. So why we are giving this is that you might be giving a function that has to be simplified. You might give a function that is too complex like this, and you have to simplify it further before you can go on to do your workings. That is why these laws are coming. So it's very important that we understand the laws much before we move on. Now, the final law is the same power law. The same power law. If you are multiplying two different functions and they have the same power, you just have to factorize that out. Then you multiply it. So I have A multiplied by B, but my A here is Q, and here too is Q. Okay, you see that the exponents are the same, but the bases are not the same. If the base were to be the same, you will just add the exponent. But here the base are not the same. The bases are not the same. It means that the exponents are the same. So you just have to factorize the exponent. So you're going to get A multiplied by B then you put your Q there. Okay, and that will tell you that it is going to give you A, B, power Q. Power Q. So this rule is also not, also have to understand how it is being used. So if you are giving let's say 5 raised to the power 2 multiplied by 2 raised to the power 2. Okay, this one, because the exponents are the same, I can rewrite this one as 2 by 2 and 5 by 2 and raised to the power 2. And that means I am going to get 10 raised to the power 2. Okay. So this is simple as that. So maybe the seventh law of indices that we have demonstrated. Then we can move on to logarithms. We can move on to logarithms and look at how the logarithms also plays.
Sir.
Yes.
Please, can we have a practical example of the rule 6, the sieve rule?
The sieve rule.
Yes, sir.
I thought I have given you an example. Okay. So let me clean this. So the sieve rule, we have the first one, which is this, and the second one, which is this. Okay. So for the first one, we are saying that if you have, let's say 16 1 over 2, this one is the same as you having the root of 16. The root of 16, and then you have the 2 here. Then if you have let's say, like another example is here, 9 half, and then you are going to have the square root of 9. The square root of 9, then the 2 will come. Okay, so that is the first one. Now the second one here, if you have 9 3 over 2, this one will give you, this one is the same as writing it, it's the same as 9 1 over 2 multiplied by 3. Now, how do we represent this one? Let's look at this. Without the 3 here, how do we represent this? 9 1 over 2. The 9 1 over 2, what do we do? This is what we have done for on it. Yeah, this one. But after this, we know that the 3 is multiplying. So you just put the 3 to the top here. So if you have 9 3 over 2, it gets same as writing it the square root of 2, then you put the 9 there, in there, then this is root to the power 3. Okay. So these are some of the examples of the rule 6. Then we can move on to We can move on to the logarithms. And logarithms are also one the rules. We finish look at the rules of logarithm indices. You can also look at the rules of logarithm. That's all. We are not looking at any complex things here. Okay, so but you have to also know what logarithm stand for. Logarithm simply means expression of numbers. Okay, it comes from two Greek words, logos, which means express, and aramos, which means numbers. So if you put expression and numbers together, it means that logarithm technically means expression of numbers. Expression of numbers. So we can use this expression of numbers in terms of divisions, in terms of multiplications, in terms of powers, in terms of root. And we can always convert them to anything that we want to do once we are expressing numbers. So simply expression of numbers is what we call logarithms. Okay. So they also note that the logarithm of a number to a given base is the value of the power to which the base must be raised in order to produce the number. Okay, so if we are given a logarithm, it is telling you that we have to find a particular number that we have to raise in order to get that particular number that we are looking for. Okay, and we are going to look at them more and more. Now, if a logarithm is standing without a base, we assume that it is the common base. And then the common base is base 10. The common base is base 10. So if you see any logarithm function standing without the particular base, without the base showing, or without indicating the base, then we are looking, we are simply assuming that it is of base 10. It is base 10. Okay, and we can clearly see the logarithm 10 base 10 base 10n base 10n. Okay, so it is telling us that we can, if the logarithm is standing alone without a base, we assume it to be a common base, and that is base 10. Okay. So from the definition of the logarithm, we are saying that if you have, let's assume you have b raised to power x be equal to y. This is a function. Okay. Then we can't, this one is the same. This is the b is the base, the x is the exponent, and then this is our y, which is the dependent variable. Okay, so we can represent this one using the logarithm. B is the base, b is the base, so we can say log of base b. B is the base, so log of base b. And then we are saying that how many times are we going to raise, b, okay, to get y? So we can say that our y is here, and this must be equal to our x. Our x. So how many times are we going to raise x or b to get our y? So we are going to raise b x time in order to get our y. So we can represent this one from the exponential form. We can transform it into what? Logarithms. Exponential logarithm. Okay. For example, let me say that we have let me say we have, if I have log, if I have log 10, and then I have 100, and this one is equal to 2. And this one is equal to 2. Now, what this one is telling me is that this one is telling me how many times am I going to raise 10 to get 100? Okay, just like here, I'm saying that how many times am I going to raise b to get y? So I say that I'm going to raise b x times. So b raised to the power x to get my y. So here too, I'm trying to say that how many times am I going to raise my base, that is 10, to get my what? 100. So we can realize that we are going to raise 10 two times. So 10 raised to the power 2 will give you 100. That is all about the logarithm. So we can use the expression, the logarithm is just about expression exponential form into logarithm form. Okay. So another example is if I have, let's say, logarithm of base 2. Okay, base, no, let me use base. Let me use base 3. Another example before we move on. So 3, then I have 9 here. So this one is equal to 2. So I'm telling myself that how many times am I going to raise the base 3 in order to get 9? So I realized that if I raise the 3 by 2 times, it's going to give you 9. So this is all about base. So sometimes we can give you this format and ask you to convert it to what? Logarithm form. Logarithm form. So if I give you 3 raised to the power 2 to be equal to 9, and I ask you to transform this one into logarithm, you should be able to do that. What you know is that this is your base, and you are looking at how many times you are going to raise your base to get your output. So you simply put log of base 3 so 9 to be equal to 2. So how many times you are going to raise your base to get your 9? Okay. So take note of how the logarithm is represented. Okay. So if you are okay here, then let's move on and then look at the natural log. Look at the natural log. So generally, we are saying that when you are writing a logarithm in the base 10 is omitted. It is assumed to be in base 10. Okay. So we now move to the natural log. The natural log, we are saying this is a logarithm. This is a logarithm to the base of irrational number. It's a logarithm to the base of irrational number. Okay. So the irrational number will be represented by E. E. So sometimes we use the E to represent the natural log. So normally we know that the log is supposed to be in the base 10. Base 10 is the common base. Okay. So if you have a log that the base is irrational number, then we said it is a natural log. It's a natural log. And this natural log has already been calculated and being incorporated into our calculators. So if you use the calculator and press the natural log, you are going to get this number. This number will come. So it has been calculated already. And then it's being incorporated into calculators and softwares that you can quickly get it. Okay. So natural log, yes. So it represented by E. So this is what you are supposed to know for now. That sometimes the natural log is written as ln n, or you can even say the ln here that we have. So it can be written as ln n or this ln n. Instead of writing it the log of E, base E, we can just simply write ln n, then we go away. Okay. So again, we are saying that there are basically two main types of logarithmic laws. We have the fundamental laws and we have the special or the derivative laws. So let's quickly look at what the laws are. The fundamental laws, first law is addition and product law. And this law can be written, says that if the base are equal, if the base of the logarithms are equal and you are adding them, then you have to multiply them. So it's a direct opposite of the law of indices, where the indices state that when you are multiplying two numbers or two terms, and two logarithms of the same base, you multiply them. You multiply them. Okay. And that is the first law of logarithm. The first law of fundamental law of what? Logarithm. So here, if you have an example, you have 5 2x plus log of 5 2. Okay, here the bases are equal. The bases are equal. So when the bases are equal, then what you do is that you multiply them, the logs. So you are going to multiply 2x by 2. 2x by 2. Then you put the log there. Log 5. So this law is something pretty that we don't need to complicate ourselves. So when you are adding two logs of the same basis, you just multiply the what? The logs and go away. Okay. Then it means that whenever the logs of the base are not equal, please don't add them. Don't multiply them. It's either you convert them to be the same log or you just leave it as it is. Okay. Let's look at the second one. The second fundamental laws of logarithm is that when you are subtracting, so here we are having subtraction and quotient law. When you are subtracting two logarithms of the same base, you have to divide them. This one is also pretty simple. Okay, so I have log 10, and I have, let me say, 20 minus log 10, I have 5. So what I will do here is that I will, because we are subtracting them, I am going to divide them. So here I am going to get log of 10, then I will divide this, that is 20 over 5. And that is all about this law. When you are subtracting, you divide. Mind you, if the bases are not equal, please don't subtract or don't divide them when the bases are not equal. Then the third fundamental law is what we call the power law. And the power law states that if you have a logarithm that have an exponent, you guys have to drop the exponent and multiply it. Okay, so you have log of q, and then you have here, let's say a and p. You see that this one is an exponent. Here is an exponent. So what you can do is that you can transform this. Just drop the p. Get the p to multiply the whole function. So we are going to have p log p log a and then q. Okay. Let's add the example that we have here. So the n here is exponent. So the m will come and drop here and multiply the whole function. So that is what we are going to have here. So if you have, for example, I am having log 10, and I have 20x squared. 2x squared. Then this 2x squared, if I want to transform this one from the law of the fundamental law of indices, logarithm, the third law of logarithm. So I'm going to drop the 2 down. That will give me 2. Then I have log 10 multiplied by 2x. So this is also the third fundamental law of what? Logarithms. Okay. So we also have the unit law. Which says that the logarithm of a unity, that is 1, if you have the logarithm of 1 to any base, then it's equal to 0. We are saying that if you have a logarithm of 1 to the base, to any base, is equal to 0. Okay. And the reason is simple. The reason is simple. If we want to convert this one, into exponential form, it is telling you that how many times are you going to raise our base x to get 1? How many times? So you can rewrite this one as x raised to the power 0 be equal to 1. So it's telling you that we are going to raise x 0 times in order to get 1. We all know that any number raised to the power 0 is 1. So that is how the law is also coming by. Law is also coming by. How many times are you going to raise x to get 1? It is 0 times. So any number, the logarithm of any base to 1, any number 1 to 1 is equal to 0. Okay, so this law is also very simple that you also have to understand. Okay. I hope you are clear with this law.
Yes, sir. Yes, Doc.
Yes, sir.
Okay.
Yes, sir.
So we now, the special derivatives of log, the fifth one is saying that the logarithm of the same base. So if you have the logarithm of the same base, it's equal to the same number. Okay, the same base is equal to the same number. Okay, so it's telling you here again that these two things, it is telling you that how many times am I going to raise x to get x. So I am going to raise x 1 times to get my x. So therefore, we are saying that any logarithm of the same base is equal to 1. And this is the fifth fundamental law. The fifth fundamental law. Okay. Now here we are talking about change of law. Change of what? Laws, base law. Now I am going to use an example somewhere to explain this too. So the next slide is the example, how to change the laws, or how to change bases, how to change the base of different logarithms. And I'm going to use this example to explain that. This example. So here we can see that this is base P and this is base Q. So it means that we have to make sure that the bases are equal. The bases are equal before we can either multiply or subtract. Now here the bases are what? Different. What should we do? Now they are saying that we should explain, or we should prove that, or show that if you multiply the logarithm of Q to base P by logarithm of P to base Q is equal to 1. Now the bases are different. So you have to, now let's explain how it the basis will come by. Okay. Now first you have to, so first let's go back to, yes, yeah, and then see how we can change the logs. So let me use this and clean this. This is self-assessment, so don't worry, you are supposed to do it yourself, but I just want to use this example to explain how you can change the basis. Okay. So if you have something like this, let's take this one first. Let's take log PQ plus PQ. And let's assume that let y let y so y to be equal to log of this QP and then Q. Let y is equal to this. Okay. So if this is the case, we are saying that how many times am I going to raise P to get my Q? How many times am I going to raise P to get my Q? So I am going to get, how many times am I going to write my P to get Q? So I'm going to raise P y times Py to be equal to my Q. Okay, so it means that I want to take the log of both sides. Log of both sides. So if you take log of both sides, you are going to get log P and then raised to the power y to be equal to log Q. Log Q. Now using the law of the power law of logarithm. So if you have something like this, you have to drop the y down. Drop the y. So you are going to get y to be equal to a y log P. Y log P to be equal to log Q. P please, what I'm doing, if you don't get, I want y to stand alone. So I will divide both sides by log P. Log P. And here to log P equal to log Q over log P. Log P. Okay, so when you see here, the first one that you have, you see that it was in log base P. It was in base P. Now it is not in base P again. It is in base 10. It is in the common log. It is in common log. Okay. Now we can do the same thing to the second one. This one. So here, what we are going to do, we are going to follow the same approach. Let me clean this and let's follow the same approach. Let's follow the same approach and say that we are going to consider the second one. And say that let y, let me say y, let y to be equal to log Q, log of base Q P. So I'm going to let y to be equal to this. Now here too, I am also going to say that, you see here, if you want to convert this one to exponential form, it is telling you how many times are you going to raise your base to get y. to get P, sorry. To get P. How many times are you going to raise your Q to get P? It means that you are going to raise your Q P times. Sorry, Y times. To get your P. To get your P. So you can take the logarithm of both sides so that this one become log QP, Q raised to power Y, sorry, to be equal to log P. Then I'll apply the power law of logarithm where I can drop this one down so that I am going to get, so that I will get I'll get my Y log Q to be equal to log P. Again, I want Y to stand alone, so I will divide both sides by log Q. So I am going to get Y to be equal to log Y to be equal to log Q, no, log P, log of P divided by log of Q. Log of Q. Okay. Now, finally, we see, let me explain things here, that you've seen that originally from the main function that we have, okay, they were in different bases. This one was in base P. This one was in base Q. But when you finally find out, you see that the bases are not there again. The base is not there again. Here, base is not there again. So they are now in their common base. They are now in their common base. Okay. But remember that Y is equal to this. And that same Y is equal to this, the final one we find here. Okay. Then here too, I also made that let Y to be equal to this one. And this same Y is equal to this. So it is telling you that this log of PQ is equal to this fraction. And then this log of QP is equal to this fraction. So I can replace them here. So let me go to here and clean this one and replace them here. Then you see the final result. So log PQ, I am going to replace the QQ by this one. Sorry, this one, log PQ. So I am going to get log of Q divided by log of P. Log of P. This one represents the first one, this one. Then the second one too is this, the one we find here. So, but we are multiplying. So you multiply this one by log of P. Log of P over log of Q. Log of Q. And they are saying that this one must be equal to 1. You have to prove that it's equal to 1. And it is obviously equal to 1. Now, first, we have done two things. First, we are able to change the base to a common base. Secondly, we are going to prove that if we multiply them, we are going to get 1. And here is how you do that. This is log P. This is log P. It will go off. This is log Q. This is also log Q. They will go out. So 1, 1, 1 here, and 1 here. So yeah, it's saying that it's going to give you 1 over 1. You multiply 1 by 1, you get 1. 1 by 1 down, we are also going to get 1. So 1 divided by 1 is equal to 1. So we have also proved, apart from converting the bases into a common base, we have also proved that the logarithms, you can change the base of the logarithm to a common base. Any question? Any question? Okay, so if there's no question, it means we have adjusted our time. This is 11 o'clock, 11:01. So we can stop here and then, God willing, meet next week again, same time.
Doc,
All right. Yes.
Doc, please, if the slide can be shared to us early so that we can practice
the slides have been shared already long time. Yes. You have it. Course rep, can you confirm that?
Yes, it has been shared.
Okay. Maybe you can reset it again. Maybe he wasn't there or he didn't see it.
All right, sir.
So if there's no question, let's stop here, then meet, God willing, next week. Have a wonderful evening, afternoon, sorry.
Thank you, sir.
Merry Christmas to you.
And same to you. You guys are enjoying your Christmas.
Christmas without money.
Without money.
Oh, the system is working. There's money.
But I've not heard a lady voice since we met. Are they not there?
Say they are there.
So why are they keeping quiet?
So we are here.
Hey, Dixon.
They are just observing things.
Let me hear from you whether you are doing okay.
So we are fine.
Who gets spoke? Is it?
It's Abba Dixon.
Abba Dixon, okay.
Yes, please.
Oh, that's fine. Good to hear that you are fine. All right. See you next week.
Okay, sir. Bye.
Bye.
Nana Papa.
That's right. Please, how can you get the slides?
The man's read it. Oh, no.